Hello there, and I hope you can hear me clearly. The Metals Technology webinar is due to get underway at 12:30, but hopefully you can see the slides. It's the slide in front of you, and it would be great if you can maybe just introduce yourself into the chat box there and tell us your sort of thoughts and views on the statement that we've put there. The webinar is due to kick off. For everyone who's thinking or asking, it's due to kick off at 12:30. Excellent, thank you, Tom. First one to come out with a thought there. Actually, a disagreement on the statement. Dependence on other countries it would lead to. Graham, your thoughts on that at this point?
Yes, I can't actually see the comment that was made, but
okay.
Yeah,
let me read it out. So Tom Green said he disagreed with the statement given the strategic weakness, i.e. dependency on other countries it would lead to.
Yes, I think I would agree that there is no answer to this question or this statement because there are many different types of steel, and what sort of steel are we talking about and in what volumes? So it's an open question, really. My own view is that the days, if we go back to Victorian times, 100 or 150 years ago, when the vast majority of steel in the world was produced in the UK, and we were the technology leaders. We had the coal, we had the raw materials and the know-how. Those days are clearly long gone. And as is evidenced now, of course, that the large number of steelworks that have had to close, even going back 50 years, the industry has reduced massively in its volume. That will never recover. We will never, as a British nation, get back to that situation. And it's not economically viable for us to attempt to do that. The technology has progressively been transferred to, to emerging nations who are exploiting it very effectively. Of course, in parallel, steelmaking technology has been developed by other countries. And the majority of steel producing nations now are able to produce high quality steel of most grades in large volumes. Where the UK has an advantage, I think, is in speciality type steels. So I don't know, do we have anybody else commenting on this?
Yeah, we've got some more comments here. So there's a lot of disagreements here coming through. So we've got Douglas coming here. He says now more than ever the UK should produce steel along with other essential commodities. And we've also got Victor van Lambregijn, who would disagree, and they say a country needs to have industries that add value. Service only moves money around. Any thoughts there, Graham?
Well, yes, I'm not an economist or a social scientist. I'm a metallurgist. So, I mean, I am, and this depends on your politics, again, so getting a little bit non-technical. My view is that to an extent, and not exclusively, we have to run our country as a business. So we can't afford the luxury of doing things simply to create employment and running what are, unfortunately, these days, not cost-effective industries. So doing it just because we can and for the sake of it, I don't think is viable. But we do, as a business, need to have things under our own control to an extent. So, yeah, we don't want to be at the mercy of overseas suppliers, and some nations will choose to switch on and switch off the supply of steel for political reasons as much as anything else. So we do need to retain, as a country, some ability. But where I think we win out is in the high tech specialized area, where we need a reliable supply of maybe small volumes of high specification material on a short lead time, and without or having it under our own control. That's my view. Okay. Speaking as a UK national, and I appreciate we have an international audience here, so I have to be a little bit guarded as to what I say.
Okay, we've got, thanks Graham, we've also got Mark Greaves coming in from Derby here. He says, I think the UK needs to produce steel, but it needs to produce it in a form that is needed at a competitive price, granted that it's easier said than done. And also, Johanna, they disagree with the original statement. Steel remains a widely used material across the majority of industries. It therefore makes sense to maintain in-house production capabilities to ensure we are not entirely reliant on imported materials. More than anything, this provides redundancy. And another one that disagrees, Thomas Payne here, he says the UK still leads in niche areas of metallurgy and bespoke application alloys. Any more thoughts there, Greg?
Yeah. No, I couldn't agree more, Thomas. I think that's what I was trying to say, that in the niche areas we do lead, and even if we don't lead, we still need to have that high added value material supply under our own control for strategic reasons, if nothing else. So I think I'm agreeing with everybody. There are sufficient international suppliers now that for the high volume, perhaps lower grade, less technically demanding products, if we can't get it from one supplier, there are 3 or 4 other perfectly viable suppliers. So international competition means that I think it's very unlikely that we'll find ourselves in a position that we simply cannot obtain the material. And of course, that international competition will drive the prices down, and it drives them down below a point at which we in the UK can produce and still be profitable. But for the niche products, that's not necessarily the case. In fact, there's a market for us to sell special grades of steel as a raw material internationally, but more importantly, to sell the products made from that high-spec steel.
Brilliant, thank you, Graham. So, for those of you just joining, we'll be commencing the webinar at 12:30 in about 5 minutes' time. But please do take a look at the statement that's written on the screen there in front of you, and make any comments into the chat box there on your right-hand side. Just any of your thoughts around that bold statement. Okay, Tamara Parker here has come in and said, we should produce steel here. It keeps people in work. If we don't, we'll be open to people charging us more.
Yeah, we're sort of getting into politics and economics again. And I mean, we all have personal views. I'm, as I said earlier, I am more a scientist than a politician, so I don't want to get too deep into that. But my personal view is there are other ways of employing people, and I think if we and I have great sympathy with the many thousands or tens of thousands of people that have lost their jobs through the progressive closure of steelworks. Certainly in my working lifetime, I'll admit to being 63 now, so I left university in 1978, and over those 42, 43 years, the steel manufacturing industry in this country has changed dramatically. And its ownership as well. Let's not forget that. When I was a young man, it was British Steel, and that was it. And privatisation has meant that the industry has been fragmented. The vast majority, if not all, of our steelworks now are actually owned by overseas companies.
Okay, well, actually, one more point here. Oh, sorry, yeah. So just from SCP, another disagreement on the statement. It's important for UJ continues steel production. It gives engineers opportunity to work with the steel industries to develop materials specific to design requirements.
Yeah, that comes back to my point again. Niche materials, specialized materials often for high-tech applications, for aerospace, for nuclear, for the very technically demanding, maybe only small volumes, a few hundreds or thousands of tons required, but of a very special grade, and for strategic reasons and economic reasons, I think that's the way to go.
Okay.
Right, let's not forget recycling.
Yes, there's actually one point here actually coming in from Stephen Hall. Producing recycled steel in the UK through EAF methods might have some benefit.
Yep.
But I feel the processing of steel into products is a stronger UK skill. Fabrication, cold forming.
Well, it does, and yeah. So there are some large suppliers of stainless steel who are using electric arc furnaces, EAF, to recycle material, and that actually is the strap line of their business is, yes, producing steel, but in as environmentally friendly a way as possible, and they place very strong emphasis on the recycling aspect.
Right. Okay. Well, thank you very much for everyone's comments there. I think that's been very useful. It's caused quite an interesting debate there already, and it could go into some depth, I think, in a lot of different areas. But I think we shall now. It's 12:30, and I wanted to kick this webinar off. So I know a number of you have been waiting. So thank you very much for everyone joining the webinar this afternoon. Today's topic is metals technology. I'm Dan Sanders, and I'm going to be the moderator for today's session. And so all the way throughout this webinar, if you have any questions that come up when our speaker is talking, please put them into the chat box, the attendee chat box, and I will do my best to filter them to the speaker throughout the session. If any of you do have any technical issues, one of our technical team will also be on hand. Just highlight it in the chat box, explain the technical issue you're having, and they will directly contact you to see if they can resolve it. Anyway, so this webinar today really is to introduce the fundamental concepts of alloy chemistry, shape forming and heat treatment processes used in all industry sectors, from aerospace to biomedical. It's going to be a fascinating talk today. So we've got Dr. Graham Small from the University of Sheffield, who's going to be the speaker for today. And I'll hand you over to him now. Graham.
Okay, thank you very much, Dan. I'm not 100% sure. Have you been moving the slides through?
I haven't, no.
No, that's okay, good.
Yep.
Right. Yeah, okay. Right. Yep, so that's my opening slide. Thank you. Yes, so thank you all for joining us today. As Dan has said, I'm Dr. Graham Small. I am a specialist metallurgy trainer, and I provide, and my team provide, metallurgy training courses on behalf of the Institution of Mechanical Engineers. Firstly, there are topics which we would regard as standard one-day, 6-hour training courses. And today I'm going to go through in 4 sections, actually, and describe the contents of those courses. And I'll hope to give you a little bit of technical information, but 60 or 70 hours worth of training, I'm not going to be able to impart all that knowledge to you in less than 1 hour. So the first section is just looking at some of the fundamental fundamental aspects of metals. Our two courses, Fundamentals of Metallurgy and Metallurgy for Non-Metallurgists, cover those topics. I will then go on to look at steels and non-ferrous alloys and how they are put together and what they do. The third section will be looking at manufacturing processes, and then finally we will have a look at aspects of in-service performance of steels and non-ferrous alloys. So, first question, why use metals? There are other categories of material that are available. There are plastics, polymers. You can make products from wood, natural materials, and ceramics, etc. But metals are so widely used because they have a combination of properties: strength, ductility, the ability to be formed into shapes. They are tough, and we will define later the differences between strength and toughness, and hardness. They are resistant to abrasion. They do tend to be quite heavy, which is often a disadvantage. They can cope with high temperatures, and they can be used to conduct electricity and indeed to conduct heat. Those are features. Sometimes that's a benefit, sometimes a disadvantage. And there are so many different types of metal and different types of alloy, it's impossible to list them all. There are many thousands. So when you say metal or alloy, you're actually talking about a very wide portfolio, a very wide range of materials. And indeed, for each of those materials, the way in which they're processed makes a dramatic difference to the final properties of the finished product. There are, in fact, something like 95 different metals, different elements. As you can see here on the periodic table of the elements, the ones we're going to focus on are highlighted with the red and blue circles. So iron, of course, there sitting right in the middle, being the basis for steels. We've then got aluminium, titanium, nickel, and other forms of non-ferrous alloy. But each alloy that we talk about will be a mixture of maybe 5 or 6 different elements, and some non-metals included as well. So for me, the definition of metallurgy really is understanding the manipulation of the microstructure of the material that we're dealing with to influence the properties. And that in turn, if you can see the triangular diagram on the screen, the properties influence the way in which the material can be processed. But in fact, processing, heat treating, forging, casting, etc., does change the microstructure and in turn changes the properties. So this triangle, we go round and round in circles. Each of the two aspects influence the other one. And that really is the profession of the metallurgist, is to understand all of this and to advise the engineers and production people on which material to use for a given application, how to produce the product from that material. So in the Fundamentals of Metallurgy training course, we will explain in fairly simplistic terms the fact that all materials, particularly all metals, are made up of atoms whose size is somewhere between 0.1 and 1 nanometers. And we explain what that means. 1 nanometer is 10 to the minus 9 meters. And just to get people to understand that we're talking about things happening on an exceedingly fine scale. And we then explain that the atoms are lined up, as you can see on the top right here, into crystals. And then those crystals are organized into grains, which are moderately large chunks of material, as you can see in the image at the bottom. And in that course, we explain the relevance between these different features of metals and alloys. There are a number of different crystallographic structures. You would think logically that if you're trying to arrange atoms to fill space, a simple cubic array would do, as seen on the left here. Actually, that almost never happens. Polonium is the only naturally occurring pure metal that adopts that structure. The whole basis of metallurgy revolves around whether the alloy we are talking about has a body-centered cubic structure with the configuration you can see illustrated there, or a face-centered cubic structure, or some choose to have a close-packed hexagonal structure, where rather than cubes, the crystal structure is based around hexagons. In fact, there are a number of other minority crystal structures. Each pure material, pure metal, will naturally adopt one of those structures in a crystallographic setup. But some materials, notably iron and titanium, actually transform from one structure to another at a critical transition temperature. And that again opens up a whole field of heat treatment technologies whereby we can modify the properties of the material by heating and cooling at different rates. So in the fundamentals of metallurgy and the metallurgy for non-metallurgists course, we explain that in more detail. And we also explain the fact that when you are producing an alloy by mixing metals together or mixing metals and non-metals, for example, introducing a small amount of carbon into iron to produce a steel, those elements are not generally soluble to a large extent. So depending on the temperature and the circumstances, iron will only accommodate typically up to 2% of carbon. And under some conditions, it's very much less than 2%. So we tend to get separation out of alloys into phases. And you can see here a picture. Some of you I know will be very familiar with this and will know immediately that that's a pearlite structure. You can see black and white phases alternating. And the chemical composition and the crystal structure of the black phase is entirely different to the chemical composition and the crystal structure of the white phase. And by carefully manipulating the chemistry and the heat treatment and manufacturing conditions, we can control the balance between those phases. And that is has a major influence, as I've said, on the mechanical properties. Also, the grain size. Each grain, this is a two-dimensional cross-section through a three-dimensional structure. Each of those grains has a number of phases and a consistent crystalline structure within it. The size and the shape of those grains will also have a massive influence on the mechanical properties of the product. So we explain how to manipulate and understand grain sizes. Just going into a little bit more depth into the situation with steel, I mentioned that iron, so on the left of the diagram here, at the origin of this plot, we have 0% carbon, so pure iron, and you can see that the gamma phase in the middle, the rhombus sort of shape, is called austenite. So that combination of temperature and carbon content shown in that rhombus-shaped area labeled austenite, that is where the carbon is dissolved in the iron, and it's a face-centered cubic structure which we call austenite. When we come down to lower temperatures, that austenite becomes unstable and it will separate out into ferrite, which you can see marked there, has very, very low solubility of carbon, almost zero, and that exists below 900 degrees C. And then on the right-hand side of the diagram, you can see cementite, iron 3 carbide, which is rich in carbon. So the stripy pearlite structure that we were looking at just now is actually alternating layers of ferrite and cementite. And the morphology of that is critical in determining the strength and other properties of the steel. And that's explained in great detail in a course, a one-day course, 6 hours, talking about different types of steel. When we come to look at strengthening mechanisms and how to control the mechanical properties, there are this is an illustration now of the crystalline structure, and you can see that there are imperfections. There is an edge dislocation and a screw dislocation where the planes of the crystal have become slightly misaligned, or an extra plane has appeared. And that is the basis on which metals deform, actually. If you bend a piece of metal or stretch it, those dislocations move, allow the atoms to rearrange themselves, and that is the basis for the strength or lack of strength of a material. So anything we can do to prevent those dislocations from moving around will strengthen the material. So again, in the steel and the heat treatment course, we look at various different mechanisms for increasing the strength. Sigma F here, you can see a little equation at the top. So the strength is the sum of the friction strength, the natural resistance of those dislocations to moving. There's a solid solution component which allows us to prevent dislocation movement by introducing additional alloying elements. There's a grain size factor. We can produce precipitates, and we can actually, by mechanically deforming, we can create a very large number of dislocations, which is another strengthening mechanism. So this is all explained in the courses that we run. If I can move on to just give an illustration of a solid solution. So here we have, for example, this could be a copper alloy or a steel, where we've got iron atoms or copper atoms in the majority, but then if we introduce another atom, it might be slightly smaller or slightly larger than the parent lattice, or and that would be a substitutional introduction, or it may be an interstitial atom. So carbon in steel actually sits in between the iron atoms, as you can see on the right there. So we need to understand all of that to understand the strengthening mechanism due to solid solution, substitutional and interstitial alloying. We also need to understand the growth and control of precipitates, such as nickel-3 aluminium, and carbides, for example.
Graham, we've got a couple of quick questions here. One of the questions is, why is dislocation necessary for the metallurgist?
It's necessary because the strengthening and control of the material and the toughening is all determined by the ability to stop those dislocations from moving, or to make it more difficult for them to move. And the way that we do that is by introducing or by constructing alloys with different combinations of metals. For example, the precipitates you can see here are nickel-3 aluminium, so we need to understand the amount of nickel and aluminium to introduce into our alloy, and then how to heat and cool it to get these precipitates. They are very tiny in this instance, to make sure that they have the correct size and volume to give the maximum strengthening effect. So the metallurgist has to understand all that, and that's what you would learn if you were to do a degree in metallurgy at university. The engineer, or the person producing the material, the steel or the alloy, or using it, probably doesn't need to know all that detail, but they do have to at least understand that all that science exists. So that's the purpose of the fundamental scientific training courses that we deliver, is to infer that basic understanding. So I hope that's answered the question.
Okay. And just one more on the dislocation side. Does a dislocation result in ductility?
A dislocation moving results in ductility, yes. So if there were no dislocations, the material would not be ductile. The more you have, and the more mobile they are, the more ductile the material. Unless you get to a point where you have so many that they actually interfere with each other, and that's the basis of work hardening, if you're familiar with that term. So particularly in cold forming, if you repetitively roll a material to form a sheet, you'll get to a point where you've rolled it so much, you've produced so many dislocations that it actually becomes brittle and the sheet will shatter. A simpler illustration of that is if you take a paper clip, straighten it, and then bend it back and forth, it will be ductile initially, it'll be easy to bend, and when you've done it 10 or 12 times, it will break because it's then become brittle. And that's due to the generation of a very large number of dislocations. Okay, so I'd like now just very briefly to describe what is contained in the training courses dealing with carbon steels, stainless steels, and a family of non-ferrous alloys. So the term steel is a very, very generic term. There are many different types of steel, and we tend to sort of subcategorize them into low alloy steels, which typically contain 95% iron and 5% of other things, such as manganese, chromium, molybdenum, nickel. High alloy steels have more than 5 weight % of those alloying elements, and then stainless steels must contain at least 11 weight % of chromium, and often they will contain many other different alloying elements as well. So the control of steel, and to understand steel metallurgy, we need to understand the role of those alloying elements, those metals, but very importantly, we have to understand the role of carbon. As I said, a 2% carbon steel would be a very high level. Typically, we would have less than 0.5%, less than 0.1% of carbon in some cases. And we have to understand where that carbon resides. This is a schematic illustration of the stripy perlite structure that I mentioned, but also there can be a tendency for freestanding carbide particulates to form, and those will also contribute to the mechanical properties of the material. So we need to understand all of that. We also have to understand the consequence of varying the cooling rate. So if we take a material up to the austenite region, which if you remember on the phase diagram would typically be around about 950 degrees C, if we cool it slowly, we get the perlite structure. If we cool it very quickly from 950, we actually get something very different. And this is dealt with in the heat treatment training course. The mechanical properties and the way in which perlite and martensite will perform in service are very, very different. And it's exceedingly important that we understand that. And we also need to understand the effect of the various alloying elements that I've mentioned. And on this slide, the red ones mean that if you have too much of these alloying elements, they will have a negative effect. So too much phosphorus or sulfur will reduce the ductility and will reduce the toughness, whereas manganese, chromium and nickel will increase the toughness. Weldability is poor if you've got too much carbon. Sulfur again is bad news. So we have to understand the science behind the influence of all of these alloying elements on these various mechanical properties. When we look at carbon content, so here we have a stress strain curve. So this is measuring the strength, the response of the material to applying a load, a tensile load, and the amount by which it stretches under the influence of that load. So pure iron will stretch to a large degree at a relatively low stress. Wrought iron, mild steel, high carbon steel, as we go up this series by increasing the carbon content, the material becomes a lot stronger. It's able to achieve higher peak stresses up to about 250 on this scale, but the strong materials will fail at relatively low strains. So that again is the role of the metallurgist to understand and control the influence of carbon content on strength.
Graham, I've got another question coming in here, if you're happy to. Can the mechanical property be changed? Can the mechanical property be changed infinitely by changing its temperature, or is there a certain limit to this change? That's from Manish.
No, there is a limit. There are upper and lower limits, but with some steels, you can change the tensile strength or the toughness or the hardness for exactly the same piece of material with the same chemical composition. If you heat it up and cool it slowly, it will have one strength. If you heat it up and cool it very quickly, it will be potentially could be 10 times the strength. So you can vary these mechanical properties by a factor of 10 in some cases. And these are reversible reactions. Yeah, go on.
Okay, a couple more questions they're coming in. Can you briefly explain the difference between austenite and martensite in service?
In service? Yeah. I will come on to that later, but very quickly. Martensite is very strong, very brittle, and very hard. Austenite is the opposite. It's less strong, but it's a lot more ductile, and it's not as hard. Austenite is tough. Martensite is not at all tough.
Okay, and one quick final one.
Yeah.
From Christopher here. What's the difference between material fatigue and word hardening then? Or is fatigue just failure due to work hardening?
Yes, it is. One form of failure through metal fatigue can be through work hardening. It's not the only. You can have metal fatigue failures because of other reasons, but work hardening certainly contributes to fatigue failures.
Fantastic. Thanks,
we'll
Graham.
talk about that at the end when I come on to in-service performance. I'm just conscious of the time here.
Yeah, no, there's a lot of interest.
Yeah, well, that's a positive, but I know some people maybe want to have allocated an hour, so I can't talk for 2 hours. Okay. Stainless steel, yeah. So here we are looking at a plot of the rate of corrosion as a function of chromium content, and you can see that it drops off rapidly, and the cutoff is generally about 11%. So for a material to be a stainless steel, it should have at least 11% of chromium. There are many different grades of stainless steel, and we have a full 6-hour training course to explain the differences between austenitic, ferritic, martensitic, and duplex stainless steels, and also precipitation hardened steels. And I apologize, I just don't have time to go into all the detail of those today. I would like to move on just quickly to touch on aluminium alloys. So these are rather different. The melting point of aluminium is 660. The melting point of iron and steel is about 1,600. But aluminium, as you'll be aware, is very much lighter. So for lower temperature applications where weight is important, aluminium may be the material of choice. And there is a systematic nomenclature for the different types of alloy depending on the principal alloying element. So if it's mainly aluminium, but the second most common is iron, then it's a 1 series, and you can see the other series here. Some of these can be heat treated, others can't, and there's a lot of science and understanding behind the different types of aluminium alloy and how you select and control them for different applications. Generally, just going down the series here, the 1000 series tend to be quite weak, low strength, looking at the strength column here, but high ductility. So they are used for certain applications. Whereas down at the bottom, at the other end of the scale, the 7000 series have very high strengths, relatively low ductilities, but they have the benefit of low mass, so they may well be used for aircraft structures where strength to weight ratio is an important factor. And in the course on aluminium alloys, we would go into detail looking at the applications in aerospace, as you can see here, food containers, takeaway meals. A lot of engine blocks for vehicle engines are cast in aluminium for weight saving. We've got here a petrol tank, actually, the bottom left. Aluminium alloys are used in architectural applications and also for automotive vehicles. Another category of non-ferrous alloys are the titanium alloys, and there are a wide range of those, many of which are heat treatable, because I mentioned briefly that iron has a transition at 910 degrees C, the basic fundamental crystal structure. Well, titanium does something similar at 883 degrees C. So we can use that to our advantage by adding different alloying elements and creating what we call alpha or beta alloys. And you can see here some of the chemical compositions: titanium plus additions of aluminium and vanadium. This one, so-called 6,4 or titanium grade 5, accounts for about 75% of all titanium alloys. It's very much the workhorse because it has an alpha and beta structure, and that's used for a very wide range of applications. Titanium is quite expensive, but it has special properties which make it the material of choice for particularly higher temperature, corrosion resistant applications, but also it's relatively light. So if you're looking at strength to weight ratio as your main criterion, perhaps a classic example is the landing gear in an aircraft, where you want it to have the strength to do its job when you land the aircraft. When you're flying, you don't want it to be too heavy because that costs you a lot of money in fuel. So you can see here for grade 5, the strength to weight ratio at 188 is very much higher than, say, stainless steel or other forms of steel. So that is where titanium alloys come into their own. And there are other applications in chemical processing. The oil and gas industry, for example, makes use of the chemical and corrosion resistance of titanium alloys. Biomedical applications, titanium is resistant to corrosion by blood and bodily fluids. So if you need a hip transplant or a false knee or something, that's very likely to be titanium. It's also used in armor because of its high strength to weight ratio and its impact resistance, and it's used in aerospace, particularly in military applications. So if you can afford to use titanium, it's an excellent material. For some industry sectors, it's simply prohibitive on cost. And then finally, we move on to the nickel-based alloys. Nickel has a face-centered cubic structure at all temperatures, as does aluminium. That means that we are limited by the way in which we can heat treat nickel alloys, but we can strengthen them by replacing some of the nickel atoms on the lattice by other metals, so using the substitutional strengthening mechanism. But the main metallurgical feature of nickel alloys is a large number of different forms of precipitate. So growing very small volumes of precipitate materials. For example, using titanium, tantalum, niobium. We can grow carbides of chromium, molybdenum, hafnium, you can see here. And sometimes we want to grow precipitates on the grain boundaries to prevent them from moving, particularly for creep resistance. So things like boron and zirconium would be used for that. And in the non-ferrous alloy course, we go through various grades of different types of nickel alloy. You may have heard of some of these: Inconel, Incalloy, 625, 718 is another one that's not mentioned here. And the different chemical additions, the alloying additions made to nickel to form these different alloys, how they are heat treated, and then a wide range of applications, very often revolving around corrosion resistance, but also high temperature. Nickel is, again, an expensive material, but there are situations in chemical processing, for example, where it really is the only viable material. It's also used extensively in the oil and gas industry. So typical applications would be perhaps offshore. Here's a picture of a submarine. Also a specialized application is in single crystal turbine blades for jet engines and gas turbines. And here the precipitation strengthening of the nickel alloys increases their creep resistance at very high temperatures, which is the limiting factor for these high pressure turbine blades. We need to have creep resistance at the highest possible temperature. The hotter you can run your engine, the greater the fuel efficiency. And then finally, this is this picture, this orange picture, is the application of nickel as the containment in a high temperature furnace. So I now wanted to move on to look at how we manufacture products from these various alloys. Most of the manufacturing processes can be applied to most of the alloys that we're concerned with varying degrees of success. And as you can see, there are 4 training courses, each of 6 hours duration, that deal with this in a lot more detail. So one way in which we can make shapes is by casting, and there are 3 generic forms of casting. The lost wax process, or investment casting, is used for the turbine blades. It's also used for things like impellers. And here we make a model of the piece that we are going to produce in wax. We then coat that wax with a ceramic high temperature refractory material. We bake that to cure the ceramic material and melt the wax. So we then have a ceramic shell with a cavity of the correct shape. We pour the liquid metal into that cavity, and when it's cooled and solidified, we smash away the ceramic shell and we're left with the solid metal product. So that is, very simplistically, the investment casting process. An alternative is sand casting for things like vehicle engine blocks, and this very large junction here for this is an offshore pipeline in the oil and gas industry. So here we make a pattern of the product we're trying to produce. We then surround that in a box, fill that box with sand with a binder. We compact the sand, then remove the pattern and put 2 mold parts together from sand, which then again enclose a cavity into which the liquid metal is poured, solidified, and when it's solid and cool, we break away the sand and we are left with the shape we require. Both of those techniques are destructive in that the mold or die can only be used once. If we go on to die casting, and this is often used for low temperature materials like aluminium or magnesium alloys, we can then use a metal die into which is machined the cavity of the shape that we require. We pour the liquid metal into that cavity. When it's solid, we open the 2 parts of the die, recover the part, but then we can immediately reuse the die by closing it and pouring fresh metal into it. So that leads itself to automation. So for large volumes of quite intricate shapes, we may well be using a die casting process. We can also inject the metal at a high temperature and at a high pressure. And we can control the temperature of the dies more accurately. So that gives us a greater degree of process control. So casting as a generic process, be it investment casting, sand casting, or die casting, has the advantages that it can be used to produce very complex shapes. You can make products close to the net shape, so there's only a small amount of perhaps machining required to get the finished product. It's applicable to a vast range of sizes from a few grams up to a few hundred tons, and it is amenable to mass production of large volumes of products. Some of the disadvantages of casting are that we have limited control over the microstructure of the product. So there is a tendency in casting for porosity to be introduced. Sorry, I'm just trying to move back to here we are. Porosity and also dimensional accuracy can suffer, because if you think about it, we've produced a cavity, we've poured liquid metal into that cavity, that liquid metal then solidifies, but all metals and alloys have a coefficient of thermal expansion. And when the material solidifies from just below its melting point down to room temperature, it will contract by typically maybe 3 to 4%. So the dimensions of the finished product are not the same as the dimensions of the model that we started with. An alternative to casting is forging. And here, this is done in the solid state, and there are two generically different forms of forging. Open die forging, which you can see here. We start with a solid billet of material. We heat it generally to a high temperature and then squash it between two dies. You can see here the black and white picture, a crude shape being formed. On the right, you can just see that we've got this right cylinder billet, and we're going to squash that down to maybe a half or a quarter of its size. Now that in itself is not making a useful product, but what it is doing is removing a lot of the deficiencies of casting. So this billet on the right will have started life as a casting. It will have been produced by pouring liquid metal into the mold, and the fact that open die forging is used to mechanically deform the material normally at high temperature to remove defects from casting, but it does not usually produce a useful shape that can be used for an engineering application. To make useful shapes, we would use a closed die forging situation. So here you can see the crankshaft from a vehicle engine, and that would be manufactured in several stages using profiled dies such as this, and you can see moving from right to left, we're getting closer and closer to the finished shape. So forging is an alternative to casting for shape manufacture. It has the advantages that it strengthens the material. You can also modify the grain size and structure. You can remove any chemical inhomogeneities. So you get a better, stronger, more reliable material from forging than you do from casting. Disadvantages are mainly to do with cost. The forging press is quite an expensive piece of equipment. The dies are expensive to manufacture and to maintain, and there are some limitations on shape. Now, I've mentioned heat treatment several times. We actually have two full-day, one-day courses, one on the principles of heat treatment and the other on the more practical aspects. Heat treatment of products is generally in manufacturing is carried out by specialist companies, and it will be done for a given product for many reasons actually, sometimes to increase the strength or the wear resistance or the ductility, to increase or reduce the ductility, the toughness, or sometimes to remove internal stresses. So if we've machined or perhaps welded a component, there will be residual stresses which could lead to failures in service. By post-weld heat treating, we can relieve those stresses. We also have opportunities in heat treatment to increase the machinability, to make a product more easy to machine. The cutting tools with which we are carrying out the machining would be heat treated to make them very hard. We can also change the surface electrical and magnetic properties. So there are many reasons and different forms of heat treatment. I'm just going to go back to the steel diagram again. If you remember, I showed you the phase diagram where austenite was the stable phase at around about 950, and it has the face-centered cubic structure. And I mentioned if we cool it slowly, we get pearlite. If we cool it quickly, we get the martensite structure. And if we cool it at an intermediate rate, we get another structure called bainite. Now, the heat treatment specialists will use a time temperature transformation diagram, and this is what you're looking at now, to understand this. So we are plotting temperature on the y-axis against time, and you'll notice this is in seconds and it's on a logarithmic scale. And this is for a particular type of steel. Every type of steel will have a similar diagram, but the exact location of these curved lines will be different. And this is showing us the temperatures at which the different phases, the austenite, the martensite, the pearlite and the bainite, are formed. So if we start at the top left-hand corner at, say, 800 and cool slowly, so we get down to 600 degrees after, let's say, 1 hour, 3,600 seconds, that would produce pearlite. If, though, we started at 800 and we cooled down to 200 degrees C in, say, 2 or 3 seconds, that would produce martensite. So it's these diagrams that are used as a roadmap for the heat treatment of steel. And in that particular steel course and the heat treatment course, we spend a lot of time explaining that and how these diagrams are used and what they mean. And this is important for the dialogue between the manufacturer of a component, the heat treater to whom he's sending his parts, and also the end user. We have to have a common language to make sure that we all understand how we're specifying manufacturing processes. So what, you might say? Yes, it's very interesting for the scientists to look at these diagrams and these fancy crystal structures. Well, the so what is, for a given piece of steel, if you heat it quickly or slowly, the hardness can change from 130 in this case to 500. The strength can vary from 300 to 1800. The ductility gets lower and the toughness gets very much lower. So I think somebody asked me before, what is the difference between martensite and austenite? Well, in most cases, austenite only exists at the high temperature. So assuming you've got a part that's operating at room temperature, it won't be austenite, certainly if it's a normal alloy steel. But it might be one of these, martensite or pearlite or ferrite. And it really depends on the combination of strength and ductility and toughness that you require. And you have the ability as a heat treater to select the heat treatment to give whatever combination of properties you want. And the final example of heat treatment for steels is normally heat treatment is carried out for the bulk of the product, and it's done in a vacuum or in air. If you heat treat in a carbon or nitrogen rich atmosphere and heat the component up to maybe 600 or 700 degrees C in, for example, methane or ammonia, which would break down to release carbon or nitrogen, that then diffuses into the surface layers, and this image here is of the teeth of a gear wheel. By diffusing the carbon and nitrogen into the surface layers, we have a very hard outer surface, which is wear resistant, but the central core is very tough. So that's another form of heat treatment. In non-ferrous alloys, heat treatment is also possible. Generally, it's for growing the precipitates and for modifying the size and shape of the precipitates. And you can see examples here of aluminium, nickel, and titanium microstructures. Just to illustrate the importance of that in the aluminium circumstance, here we are looking at as a function of time. So we've heated the aluminium alloy up, this is, let's say it's a 2000 series which has aluminium and 3% copper. Now at a high temperature, that 3% of copper will dissolve in the aluminium at around about 500 degrees. So we heat it up to that temperature. We then cool it very quickly down to room temperature, and the copper is maintained in a supersaturated solution. It's a non-stable solid solution within the aluminium at room temperature because we quenched it down from a high temperature. If we then age it at 180 degrees C, let's say, we will then start to grow precipitates of copper aluminium 2. And you can see here the dotted line shows the average particle size, and after about 10 hours at 180, the particle size increases and increases and increases. The solid line, starting at 400, shows the strength of the material. As the particles increase in size, the strength goes up, and then we reach a peak, and if we continue to age for too long, the particles become too large and the strength decreases again. So a heat treater would understand this and would know what combination of time and temperature to get the optimum strength of his material. And again, that's covered in great depth in the aluminium training courses that we offer. When we come to machining to get the very fine detail of a shape, we are now looking at the interaction between the substrate, so shown in blue here is the material that we're machining, and the black triangle is the cutting tool that is removing material. And in this picture, we're looking at the turning operation. So the cylindrical component is rotating, and the cutting tool is being forced into it and peeling off the material. Another form of machining is milling, where here we've got a similar kind of situation, but generally the workpiece is stationary, or it may be moved in the X or Y direction. The cutting tool is rotating, and it has a number of cutting edges. So on the right hand side you can see here where the cutting tool is removing chips or swarf of material from the workpiece. Now, there are limitations to the speed at which we can remove material. For economic reasons, we want to do the machining as quickly as possible and have the highest possible metal removal rate. But that will generate heat through friction. And that heat, as you can see illustrated here, will start to generate in the cutting tool, but also in the substrate that's being machined. And if you think back to the heat treatment, we are now taking the material into a high temperature region. We're going to modify its mechanical properties, which we do not necessarily want to do. We will also have an element of, in the remaining material, that after the machining has been carried out, there will be residual plastic stresses embedded in the product, which can lead to mechanical distortion, dimensional distortion after machining. So we have to understand the machining process and the limitations imposed by temperature and plastic strain, the limitations that are imposed on the machining rate. And you can find that very crudely you can categorize materials into how easy they are to machine. So low carbon steels are free cutting and easy, alloy steels less easy, austenitic stainless steels, the yellow bar in the middle, moderately easy. And as you get to the titanium, nickel and cobalt based alloys, which have excellent high temperature and corrosion properties, unfortunately they become less easy to machine. So when choosing a material, you have to balance these various factors. I now wanted to talk briefly about welding. And as you will all be aware, welding is a process by which we join two pieces of metal together by melting the interface between them and allowing it to solidify. So in effect, it's a kind of a casting process. There are several forms of welding. I just want to talk briefly about two. The very common manual metal arc welding process consists of striking an arc using an electrical power supply between a feed rod and the substrate that's being welded. That feed rod melts and becomes part of the weld pool, so the rod here actually becomes part of the weld metal, and it's coated by a flux, a material that will melt and then evaporate to form a gas shield which prevents the liquid metal from becoming oxidized, because this process is used normally in the open air and often out in the field, for example welding together gas pipelines in it could be in Siberia or in the desert or somewhere. Manual metal arc welding is a portable technique. Tungsten inert gas welding uses a similar kind of setup. Here we have an electrode and we're striking an arc between the electrode and the parent plate. But in this case, the electrode is made of tungsten metal and it doesn't melt. Tungsten has a very high melting point and it's simply there to conduct the electricity to form the arc. And rather than having the flux, we now have a flow of inert gas, normally argon, down the annular gap between the nozzle and the filler rod, and the tungsten rod. And we very often will be feeding metal into this weld pool using a filler rod. So that's another way of manufacturing a weld. Now, all welding, as I said, is effectively a casting process. If we look at a cross section now between two plates that have been welded together, you can see very clearly where the material has been liquid and where it's not been. And you can see perhaps a grain structure within this weld metal. The zones immediately adjacent to the weld metal, the heat affected zone, will not have been liquid during the welding process, but they will have reached very high temperatures. So they will have been heat treated, not deliberately, but because the consequence of welding at high temperatures forming liquid metal, inevitably that metal solidifies and forms a cast structure in the weld pool, and it forms a heat treated or heat affected zone adjacent to the weld pool. And that heat affected zone can have a variety of different grain structures, and the mechanical properties will have been compromised. If you've got for example, a martensitic steel, if you then weld it, the heat affected material will have been taken to a high temperature and then cooled slowly, so the martensite will break down to austenite, which will then form pearlite on cooling. So where you thought you had a strong, brittle martensitic product adjacent to the weld, you've now got a weaker but more ductile product. So you've changed the metallurgy in welding. When I talked about thermal contraction in casting, the same is true after welding, so we will have distortion to deal with. And also, very importantly in steels, we have to be very careful to keep any hydrogen away from the product. So in the manual metal arc process, where I mentioned that we have a flux coating, those welding rods have to be heated in an oven for about an hour at 200 degrees C to drive away any water, because any water or moisture will break down, form hydrogen, which then migrates into the weld pool and will very significantly weaken the structure. And in fact, that was the course of the British Petroleum Foinaven failure, which was a very famous failure. It's cost a very large sum of money, and that was due to hydrogen embrittlement in a weld, which wasn't picked up, it wasn't detected. The product, the manifold, went into service and subsequently failed. So a lot of this, the processes and the materials that we deal with have to be carefully controlled and understood for very good industrial reasons. The products that we're using are expensive. If they fail, those failures are extremely expensive. So that brings me to the final session on in-service performance. And here we have 4 training courses where we look at the techniques for measuring mechanical properties, corrosion, analysis of failure, and also microscopy and metallography for forensic examination of failed products. So in the mechanical testing module, we look at the stress-strain curve that I mentioned earlier, how that's carried out, and how from one test we will get a characteristic curve representing the strength of that material. And we can actually, from that, understand the ultimate tensile strength, the yield strength, the Young's modulus, and the ductility, and the transition between elastic and plastic behavior. So all of those terms are defined in the training course on mechanical testing. Just to give you some feel, the tensile strength is relevant, of course, in things like bridges where these cables are supporting the weight of that bridge. So in choosing a material from which to make these cables, we want to make them as lightweight and as thin as possible, but we have to understand the intrinsic strength of the material so we can calculate the weight of and the thickness of cables to use. We have to understand the ductility, the amount by which the material will deform under mechanical action. For example, in deep drawing this drinks can, other suppliers are available, sometimes alcoholic. That can has been produced by deep drawing a disc down into a punch and die to a wall thickness of less than 0.5 millimeter thick. So the aluminium alloy from which that drinks can is made has to be extremely ductile to be able to deform into that shape without tearing and rupturing. And the Young's modulus I mentioned is the amount by which a material will deform and then spring back to its original shape, so elastic deformation. This railway bridge, when a train goes over, it will inevitably bend to an extent, but we want to be sure that it springs back to its original position, and we need to know the extent to which it bends. So that is all of that we can learn from the tensile test. Another form of testing is to measure the hardness, and this is done by, well, several techniques, the Brinell, the Vickers, or the Rockwell test. And here we press an indenter into the surface of the material with a known force. In the case of Brinell, it's a spherical indenter which makes a circular indentation. We measure the diameter of that indentation, and that allows us to calculate a hardness number. So that's how hardness is measured and communicated. And I mentioned earlier that it's an important parameter in gear wheels, for example, the combination of hardness and toughness. Toughness is measured in a Sharpie impact tester, and here we take a standard test piece of material, we clamp it in a support, and then allow a hammer of known weight to swing from a known height. It swings down, it breaks the sample, and continues its journey to a lower height, H2. And if we know the mass of the hammer, we can calculate the potential energy that was used to break that test piece. So toughness is measured and quoted in units of joules. And in the case of the toughness test, we have to be aware that toughness is very much dependent on temperature, particularly for body-centered cubic materials. So for mild steels, for example. And if we make that toughness measurement at a range of different temperatures, you will see that there is a critical temperature known as the ductile to brittle transition temperature, where the ductility and the toughness drops off significantly. So we have to be aware, if we're making a product, say at room temperature, 20 degrees, and measuring its toughness, if it then goes into service at maybe -50, which are the sort of temperatures that we see in the Arctic and Antarctic, They're also the sort of temperatures we see at cruising altitude for aircraft. We have to be aware that the toughness property will have changed very dramatically over that temperature range. We also have to be aware of creep. I mentioned creep in the context of the turbine blades. Creep is the tendency for metals to deform over long periods of time, often at moderately high temperatures. And that deformation occurs at stresses well below the yield point. So the tensile test would lead you to believe that that material is not going to deform. But other mechanisms come into play, and creep has to be measured to understand the circumstances under which long-term deformation happens. And it can result in unexpected failures where, if you rely solely on the tensile data, you would say this heat exchanger boiler is not going to fail. Well, actually, it's subjected to long-term stresses at reasonably high temperatures, and in that case it did fail. So we have to be conscious of that. And finally, somebody asked a question about fatigue. There are test procedures by which we can simulate in laboratories the cyclic loading and unloading of a product, either in a systematic way or, in the case of the picture here of a railway bogie or other applications, the stress is coming on and off in a fairly random way. And there's quite a lot of understanding required to be able to understand the number of cycles, so shown here on the x-axis, the number of cycles that a material will withstand as a function of the stress that's applied. And different categories of material, body-centered cubic materials, so steels generally, tend to have a limit here. So if you subject them to stresses below that limit, you can cycle them for many millions and billions of times. But other materials like nickel and aluminium, for example, they will continue, the curve continues down. So even at very low stress levels, they will be subjected to fatigue failures eventually. The presence of corrosive media such as seawater makes fatigue resistance even more of an issue. And just one example of where fatigue was a problem, just about 20 years ago, there was a railway accident in Hatfield, just north of London, in which unfortunately 4 people were killed, and that was due to metal fatigue of the rails, which had not been detected and not been predicted. And then finally, we look at corrosion. So corrosion is a big problem. All metals, with very few exceptions, things like gold and platinum, have a tendency to corrode. They occur naturally as oxides or sulfates, and they want to revert to becoming oxides, etc. And if the material, the metal, gets converted to an oxide through oxidation, it's no longer contributing to the mechanical performance of the metal component. And there are many different forms of corrosion. I think there are 8 or 9 that I've listed here. You may be familiar with stress corrosion cracking, galvanic corrosion, where we've got 2 dissimilar metals in electrical contact. One will cause the other to corrode. We've got microbial action under the sea. We've got crevice corrosion, different forms, pitting corrosion, which is a big problem potentially with stainless steels. So in the corrosion, combating corrosion training course, we go into great detail on all these different forms of corrosion and where they are relevant. So in the oil and gas industry, we've got sometimes carbon dioxide and or hydrogen sulfide present, as well as the chloride ions in seawater, and that is quite a corrosive environment. So there's been a lot of study on the corrosion in offshore environments. Aerospace aircraft are subject to corrosion. It's also an important limiting factor in things like power generation, nuclear power stations and conventional power stations, corrosion is a limiting factor. But the good news is there are many different forms of corrosion. There are also many different mechanisms by which we can prevent or suppress corrosion. So in that course, we look at self-passivation, we look at different forms of coating, anodic protection, galvanizing, etc. Far too many for me to describe today. So that brings me to the end of the presentation. I apologize, I've overrun slightly, mainly due to the breakdown we had technically. So I hope I've been able to explain to you that metal alloys still dominate most engineering applications, and there are a very wide range of them to choose from: steels, aluminium alloys, copper, nickel alloys, etc. They all have different characteristics, different chemical formulations, and the way in which they're heat treated is essential to understanding which material to use in which application and how to produce products from those materials. I would hand over to Dan now, and I'm sure he will just mention that we have scheduled in London a number of courses over 1 or 2 days in the next coming months. And we also will be running these same courses online in a virtual classroom as we have been today. So thank you for your attention. I'm happy to take any questions, and over to you now, Dan.
Okay, yeah, thank you very much, Graham. Yep, so fascinating subject there, and some very good in-depth sort of views on this and subject matter presented there by Graham. As you can see, we have got courses coming up over the next couple of months that you'll be able to attend in a face-to-face environment. But again, these courses will be able to be delivered virtually as well. So if yourself or you're within your organisation would like to have more detail on these courses, please do drop us a line. And I was also I'm putting into the web chat there, the attendee chat, access to the recordings and the slides from our webinars as well. But yeah, so thank you very much for all attending. And yeah, and hopefully we'll be able to see you or maybe attend one of the courses in the months ahead. Okay, thank you very much.
Could I just mention in closing, Dan?
Yeah.
Have we? Oh, we're still broadcasting. Yeah, we're also very happy to run bespoke courses in company. For if one company has an interest in a particular course, we can either visit you physically or provide an online course for that company only. And in that circumstance, we can be a lot more open in the discussion and address particular issues for that business. So again, thank you all for your attention.